Hello folks, and welcome to this lesson on resonance. By the end of this lesson, you should be able to predict whether a molecule has resonance structures, explain the effect of resonance on bond length and strength, and explain the effect that resonance has on the structure of benzene using physical and chemical evidence. Now, to start this lesson and discussion, we're going to start by looking at ozone. So ozone, which is O3, if you take that Lewis structure and start to draw it, here's what the molecule looks like after you're finished distributing all of the electrons. Now, based off of this particular structure, you should know that we're not quite done yet because this oxygen in the middle only has 6 valence electrons attached to it instead of its 8. And if you have done all the stuff on formal charges, you'll also know that if you calculate the formal charges, it's not favorable, and that's why you try to get to 8. So, in that case, what will happen is that you'll have a double bond form between that central oxygen atom and one of those oxygen atoms, but when you think about it, which one does it go with? Does it go with the left or does it go with the right? Theoretically, either one would work. So if we take care of that whole octet rule thing, you will end up with these 2 possible structures. But the thing is that when you actually do a little bit more investigating and testing out with that ozone molecule, there are physical and chemical evidence pieces that suggest that what you get is not either one of these. It's not one that gets flipped. It doesn't exist as an oxygen double bonded with an oxygen, and then that same oxygen being single bonded with an oxygen. It doesn't work out to actually be that single bond, and one of them is a single bond, one of them is a double bond thing. Instead, what the evidence actually shows is that you have your oxygen. This one's going to have its lone pair. You have your oxygens here. And yes, there is one bond between that central oxygen and each of the terminal oxygens, but this second bond's worth is actually distributed between the 2 bonds. So between those 2 oxygen-oxygen bonds. So you actually get a structure that's somewhere in between these 2 and not actually either one of them. And it's not that they're flipping between one and the other, it's actually a mix of them all. And so that's why when you do have these structures that can have resonance structures, you should be drawing all of them and then indicating that they are resonance structures using the proper kind of arrow, or you can use this dotted line system to show where that the shared electrons in that other bond is being shared. Now, if we're going to take a look at this molecule and look at the sigma and pi bonds and what's going on there, what you actually end up seeing is that, yes, there is a sigma bond between those 2 oxygens, and there is also a sigma bond between those 2 oxygens. Since there isn't just one bond between the oxygens, there is going to be some pi bond stuff going on. And so what happens is that you have those pi, or a set of pi orbitals from the one oxygen, and there's going to be another set of pi orbitals from that oxygen, and you do have that pi bond being formed when those 2 overlap. But in this case where you do have a resonance structure, it actually turns out that we are going to see another pi orbital being drugged into all of this, and actually all 3 of them are being overlapped together. So this is, if we're going to look at that other drawing, this bit, which is that pair of electrons that's not in a double bond with just one set of those oxygens, but is actually shared over all 3 of them, this is where that overlapped pi bond that encompasses all 3 of those oxygens, that's where those 2 other electrons are. Now, there's a reason for why this particular situation, where you take this extra set of electron pairs and you share it over all 3 of them, it makes sense energetically. Whenever you have a double bond or a triple bond, you have a high concentration of electrons in one spot. And this actually does attract different particles that will make certain reactions happen more easily than it would if you only had a single bond. So if you are spreading out that other electron pair, you're actually going to be decreasing the reactivity of the entire particle as a whole. Now, this phenomenon where you have an electron pair that's shared over more than two atoms is referred to as delocalization. So delocalization is when you have the electrons being distributed over more than two atoms. So if we're looking at the ozone that I showed you a little bit ago, that whole having that pi bond that goes over those three oxygens, that concept is referred to as delocalization. Resonance refers to the fact that when you do have this delocalization happening, the actual structure of the molecule itself is the combined version of what it would be if you didn't have delocalization. As I mentioned, there is proof that delocalization happens, and we'll take a look at how it goes when we're comparing oxygen gas, ozone, and hydrogen peroxide. So if you take a look at the structures of these three molecules, you're going to see this. So when we're comparing the oxygen-oxygen bonds that you can find in these three molecules, you have a double bond in your oxygen gas, you have a single bond in your hydrogen peroxide, and we have that delocalized bond thing happening in the ozone. Now, if we look at the bond lengths of these oxygen-oxygen bonds, you will find that the bond length of your oxygen-oxygen single bond is longer than the bond length of an oxygen-oxygen double bond. And if you're in the IB program, you will find that the bond length numbers are actually in your data booklet, and you can see these numbers for yourself. The reason for why the bond length of your oxygen-oxygen double bond is shorter than your oxygen-oxygen single bond is because your oxygens, when you compare them to each other, they have the same effective nuclear charge. And they are also positively charged. And then the electrons that are a part of the bond that are between those two nuclei are negatively charged. Now, remember that when you have particles that are opposite charges, they attract each other. And if you take a look at what's going on here, you look at this oxygen-oxygen single bond, you have the positive charges, and then you have electrons in the middle. However, when you have that double bond, you have more electrons between them. And so because there are more electrons between these oxygens, these electrons attract each of those nuclei harder. And so because there is more attraction from that double bond, that's why the bond length for your oxygen-oxygen double bond is shorter than the bond length for your oxygen-oxygen single bond. So if we are thinking about ozone as being this molecule where it does flip-flop between one of these structures and the other, or it is just a structure that has one single bond and one double bond, however you want to think of it in terms of that, then that means when you look at a particle of ozone, you should have one of those bonds being the same length as a single bond, and the other bond having the same length as a double bond. But that's not actually what happens. What happens is that in that entire ozone molecule, the bond lengths between the central and the terminal oxygens, they're all the same, and it's actually in between that oxygen and the double bond and the single bond. In fact, the number turns out that it's more like a 1.5 bond, because that second bond's worth is distributed over two bonds. So you take that one and you split it in half. Now, if you had resonance structures where the bond is distributed between three molecules, well, then each one would be 1 1/3 bond length, or so on and so forth. Now you also see the same sort of pattern happening when you're looking at bond strength. So how strong it is, how much energy it takes to break a bond. So in terms of bond strength, your oxygen-oxygen double bond is going to be the strongest because there's such a high attractive force. It will take more energy to cut that. Your ozone is going to have something in the middle, and it is basically going to be the strength of 1.5 bonds. And then your oxygen-oxygen single bond is going to be the weakest of the three. Now I know in the beginning I said that I would have benzene in this particular lesson, but it's turning out to be a little bit long, so I'm going to set that aside for a different lesson. So I'll see you next time.